Hello, everyone. Today I have the opportunity for sharing something that is quite exciting because it's something I've been doing for many years, and I consider myself to be an expert in this field. Speaking, I think I've seen more than 3,000 of these type of reports, and so I would love to share some insights about clinical perils and dot connections. Many people they miss because, of course, you have to see a lot of them to start understanding certain patterns. And now that I've been able to grasp many of these aspects by seeing many of these reports, I think it's time to share this with everyone else. So without further ado, I would like to introduce this class to you that is about metagenomic microbiome analysis, or what I call the microbiome analysis world. So there's a couple of things that I like to mention firsthand. First of all, why it's so important to test. It's not just because we need to test whenever there's a certain reason, whenever there's a certain benefit in terms of the testing. If not, doesn't make any sense. We test for finding certain information that is going to be useful for putting together a treatment plan. So there's a lot of testings out there. And I always mention this, that if you're going to be testing just for the sake of knowing something, but at the end of the day, that piece of information won't affect the direction of your treatment plan, doesn't make any sense. For that, you have research, you have some type of instances for analyzing things that are not really going to drive the fundamental difference. But if you have the ability to understand something more in depth and you have a diagnostic or an assessment tool that will make a difference in your treatment plan, well, I think it's going to be valuable, the investment and the time for getting that done. And for the microbiome analysis, I've seen that conversation a lot. A lot of people are saying that microbiome analysis are worthless and that doesn't really make any difference. It's not going to drive any changes in your treatment plan. And I would say that that's not fully true. It will be true only if you're analyzing the microbiome with the wrong method, or if you're not knowledgeable enough to understand the information that is presented. And again, this is out of criticism, just pure information based on scientific data. So when you analyze the microbiome, you need to understand how you're analyzing the microbiome. And there's many testings offered out there, and not all the testings are made equal. The first one I want to mention is one that is quite famous, which is called 16S rRNA analysis. This is a 16S amplicon methodology that became quite trending over the past years and has been promoted as a very accurate type of testing. And the reason why is because they say that they're measuring a living type of genomic information that is only going to happen with the beings or the microbes that are alive in your body, and it's not going to relate to things that are dead. Because, of course, RNA occurs when you're transcripting genomes, and it doesn't occur on dead organisms, which is somehow true. I mean, it is true, but it's not the main reason why I don't really encourage people to use this 16S or encourage people using 16S. The reason why I feel this is not the best testing available is because it's only covering 1 to 2 hypervariable regions on a gene. So in other words, you're taking only a fragment of the full genome. And from those variable regions that they tend to vary in a certain way depending on the type of species we're analyzing, the type of microbe we are analyzing, we make the assumption that everything else relates to that specific bacteria or microorganism we're reading. And then, of course, by assuming that, we might make a lot of mistakes because we're not really reading the whole genome. We're just reading a fragment, just trying to look at someone's picture and identifying someone's face. but just looking at one eye, maybe an ear, just because it kind of matches to the person we're trying to identify, we will assume that everything else is really related to that person as well. It doesn't really make sense. So that makes a lot of misdiagnostics, assessments, and a lot of misinterpretation in the reading of the analysis. So the 16S is just a region that you can check in rRNA material that varies depending on certain type of microbes, of course, and that because we have certain data that certain microbes, they tend to have certain type of variations, we would assume that that relates to that specific microbe. And again, there's a lot of overlapping. So those targeted regions are not the only ones which are varying in terms of the type of microbes. And then we have other types of variations, and things get a little bit messy. We might not get the right microbe by just reading those targeted regions. That's why I don't really encourage reading this type of analysis, because we might see things that are not really there, or we might not see things that are there, and we might get a wrong idea of the composition of our microbiome. And if we care so much about living or not living, that's something that we can also argue that's not totally important. And just because a lot of things are being used or they're creating certain reactions or imbalances in the gut are actually dead. There's a lot of genomics. There's a lot of genes that are just being read or passed or analyzed by our microbiome or by our cells, or those proteins are making reactions in one way or the other with the immune cells, and they're not necessarily, they don't need to be alive. So it's important to know these genes, even though they might be dead, but we need to know really who they are and not just assuming who they are. And for that's why I would like to have full metagenomic analysis done. Now, when we look at the taxonomy level in terms of understanding how we read microbes and what we're looking at in the microbiome analysis, we need to understand that most of the times we're seeing things between the phylum level and the family level. That's typically what we can do in terms of analysis for creating averages. So when you see any score, any range, any pattern, that patterns comes from averages, and those averages, they have to be related to a certain type of analysis, a statistical analysis that was done in a population that we all share some similarities. That's the only way we can standardize and get some patterns there. So we can't really get standardization or correlation beyond family level. So if we go more specific than that, we are very unique one to another. So we don't really correlate with our neighbor or our other family members in terms of the genuses and species that we can find in our microbiome, regardless of the type of microbiome we're reading. More specifically, although it's in the gut, in this case. But most of the times we can't. And so all the comparisons, all the statistical analysis are done up to usually family level analysis. We can read, of course, and we can identify species and strains through all of those species. That's fine, but we can make correlations. So one thing when you see a microbiome analysis is the scores, the ranges, the average populations, and how much you're feeding in those populations and how off you are, how close you are to those ranges. And that is typically analyzed up to a family level. And then you will have a unique list given for example, identifying potentially pathogenic species, etc. That is something that is unique to you and can be compared to someone else. They do like to do that in a certain way and try to compare anyway, but it's really not comparable because we're quite unique beyond the family level. Now, and again, my preference is the whole genomic thing. And that is because we're reading the DNA sequences from end to end. So we're not just grabbing piece of anything in terms of the genomic sequence. We're just grabbing the full sequence and we're reading that from A to Z. So we have the complete puzzle. We have every single piece of the puzzle. In terms of identifying a face, for example, we have every single piece of the face. So we don't have to really assume that relates, that ear and that eye we're seeing from the picture relates to someone's face, but we don't really have the rest of the picture. We have the whole face. We can properly identify who that person is, or in this case, who that microbe is. And we can analyze very specifically up to strain level. We can make very proper identifications in terms of what is a bacteria or viruses, fungi, and protists. We can differentiate them pretty well. And as an accuracy, with that probably the most outstanding accuracy in the market, with a 99.9% specificity and more than 95.7% sensitivity. It's pretty reliable when we look at this information to know that we're seeing what we're seeing, and it's not something else. Now, that will depend also if the full sequencing is done with the proper methodology. And that means that we're using the type of method that will allow us to identify these and read these genes from end to end with the proper depth. That's a conversation we're going to explore in a little bit, but just giving you a few ideas that we also need the type of depth or the type of specificity in the reading that allows us to understand the full genome sequencing, because we can do it more like a superficial reading. And there's sometimes the way we sample that, or we process the sample, or the way we take the sample in the first place, that might create some variations. So there's a very specific way we have to do things from the beginning, from the way that the sample is collected until the sample is analyzed, to guarantee that the process will come up in the way we want with the right accuracy and not compromising that by any means. Now, the benefits of stool testing analysis is that the GI tract is an open but also closed system. So even though things are coming in and coming out, so it is just the outside. It's like I always say, it's kind of like putting a straw inside the muffin. You're connecting the outside with the outside, but you're going inside the muffin with the straw. Still, it's a closed system in many aspects because you have sphincters and you have certain different areas that they're regulated by multiple ways and multiple fluids and organs and, again, anatomical structures. So it does create good place that you can analyze things that are passing through, things that are living there, and we can get a good sense of what is going on there if we analyze everything properly. So this tube, it's actually pretty good for being analyzed. And that's why we have so much information about it. And just ironically, one of the niches that we knew the least and we still not know that much compared to the GI tract is the mouth. And I'd like to mention that because this is my background in dentistry. And interestingly, this, which is very easy to read, it's open. We don't have that much information compared to the GI tract. Anyway, hopefully we're going to get there and we're going to get more information in the mouth cavity because it's so critical. And you're going to see some aspects of this in a minute when we look at the microbiome compositions in the gut, and you will see some cool things that are related to the mouth as well. So the main features of microbiome testing, first of all, we want to see diversity. And diversity has two components usually. And this is something that comes from ecology analysis, is not really specifically related to microbiome analysis. Any type of ecological analysis has a diversity component, and you usually can be split in two aspects. One is alpha diversity and the other one is beta diversity. Well, alpha diversity is more like a quantitative analysis. So literally you're counting microbes. You're seeing how many microbes are present in that ecosystem, and that amount will become your alpha diversity. And in the microbiome of the gut, we want to have a good amount of alpha diversity, meaning that we want to have good amount of microbial species detected there. If we are running short in the amount, means that we had some disruptive agent that is affecting the amount and therefore counteracting the normal growth of the microbes that are living there. Now, that applies to the gut. If you go to other areas of the body, you don't want to have alpha diversity too high. For example, the vaginal microbiome needs to be with a low diversity to be healthy. And so alpha diversity being high and correlated with healthiness of that ecosystem mostly relates to the GI tract, especially I will say to the colon, because also in the small bowel, you want a good amount of diversity, but also not that much, because we know that that drives other imbalances. So we're mainly looking at colonic diversity here. And alpha diversity, again, typically relates to the amount of microbes that we find here. And we assume that if we have a lot of microbes, we have a lot of functionality, because more microbes, we have more genomic information or more diversity in the microbes that we will need for various specific functions. And if we have many of them, well, we have more abilities to perform with different type of genomic material, more knowledge, quote, quote, knowledge, and therefore more abilities for performing functions. But that also needs the other side of the coin, which is beta diversity. So beta diversity is a qualitative analysis. So it's looking at the types of microbes that are living in the microbiome. And so we don't have really a number here. What we know is that there's a certain pattern in the composition of the microbiome of the gut or any other microbiome that we can say is the standard or is close to what we'll see as healthy. In other words, we will know that that pattern will correlate to good functionality of your microbiome. And it might vary a little bit. It doesn't need to be always exactly the same for everyone, but we have a certain tolerance range that we can analyze. And if you have a good composition pattern, meaning that you have the right types, and then you also have the right amounts, your overall diversity becomes sufficient to perform with the right type of functionality or with the right efficiency in your functionality. So we need both aspects. And again, this applies mainly to the colon. Don't try to correlate this to other areas and sometimes to other microbiomes, because it's a little bit different. Also, this is typically related to adult microbiomes, not for kids or toddlers or infants, because they're in the development phase, and that diversity tends to change over time. And there's a great class that Star Edwards did for Microbiome Labs, I think a year ago. It's about the development of the microbiome of in humans, and that will give you all the information in terms of how our microbiome is evolving to become a fully adult microbiome. And now we can know what patterns we're going to be expecting if we need to do a metagenomic analysis for the microbiome earlier, before the microbiome becomes a grown-up microbiome. Now, when we look at the phylum level analysis, there's some things that are really interesting. So we have two major phylums making the microbiome of the gut. One is Bacteroidetes and the other one is Firmicutes. Those two are big. They make more than 90% of the total composition of our microbiome. And remember, taxonomy level phylum, it's kind of like a large group. It's not very specific, but it's a really good way for understanding what we have and what type of balance we have. And actually, we can even compare Firmicutes to Bacteroidetes, and that's what is called the FB ratio, which has certain correlations with metabolic disorders and other type of metabolic conditions. Then we have two small groups that are also constant, actually three, but I will leave the last one for the last. We have Proteobacteria and Actinobacteria. So Actinobacteria and Proteobacteria are small groups. They're not really abundant, but they're very important. They play a very important role in the balance and the functionality of the microbiome, but we don't need that much. We need just small amounts of them to be present in the gut microbiome. And then we have another one that is called, it's more inconsistent, but still very needed, especially because of one Keystone species that belongs to that phylum, which is Verrucomicrobia. Verrucomicrobia, it's an anaerobic, strict anaerobic group of microbes, and it has a family inside that is called Akkermansiae. And Akkermansiae has a Keystone species inside that group that is called Akkermansia muciniphila. And I'm pretty sure that a lot of people, all of you, have heard about that, and it's very important because it plays a lot of metabolic roles in the gut, and therefore we want to see some Verrucomicrobia detected because that will relate to a potential presence of Akkermansia muciniphila. So in the phylum level analysis, we expect to see Verrucomicrobia in a small amount, but still significant enough to bring those microbes in our populations. The other two, proteobacteria and actinobacteria, are very important, but as everything else in this world, the key is balance. So not because something is good, more is better. And actually, for all these microbes, we want to be in a certain degree of balance. We don't want to be too high. We don't want to be too low. That's what we call a good diversity level, when we see all these populations present in the right amounts. And that's exactly what we're talking when we were explaining beta diversity. Now, there are some other groups that are not supposed to be there, but they might show up. And I will highlight a couple of ones right away because they're quite associated with a few things that you really need to look after. One of them is called Euarchaeota. And this is a group that holds a lot of families that are typically methane producing agents. So we probably, all of you heard about methane and the correlation with SIBO. Well, methane it's not just a mean byproduct that is made by certain nasty bacteria that they're there just to make us sick and create SIBO symptoms. That's a complete lie. Methane, it's a signaling gas, like nitric oxide, for example. Methane plays a role in signaling the brain and tells the brain that peristaltic movements and actually all the motility in the gut needs to be stopped, or at least pause for a certain amount of time. And why methane is doing that? Well, let's imagine you ate a big tomahawk steak, which is pretty yummy. And you grab that steak, which is very complex to be digested. You're going to release through the digestion of those proteins something called TMA. TMA breaks down and becomes methane through an enzymatic process. Now, why these TMAs are being released after eating this big chunk of food, especially protein-derived food, and becomes methane? Because this is very complex for the body to be digested. So for getting that done, we need more time. So methane is a timing controlling agent. What it's doing is stopping things for a minute, leaving that food for a little bit longer so we can properly digest it, and then should be reversed and let things continue its path, and just digestive process wise, everything should be normalized. But some people are constantly producing methane and they have elevated Euarchaeota populations. And that is because those people, they need constantly more time for digesting their foods properly. And that is related to digestive deficiencies, meaning that your liver, your gallbladder, your stomach acid production, your pancreatic enzymes probably are not working well. And that's what is read when you take a SIBO testing. Now, is it the bacteria that are producing these type of issues? Well, that's more the consequence. The overgrowth is more related to a compensation mechanism driven by a lack of efficiency of your support organs and your digestive organs, which are the main target if you want to improve these type of issues, not the microbes itself, because the microbes are going to get regulated, self-regulated, if you fix the functionality of these organs. So now you can try to see a little bit SIBO on a different angle. Now you can do in the same slide you will see now, but this could be different for everyone. But you see something called synergistes there. So synergistes are typically found in the mouth, not really in the gut. They don't really belong there. So if you find synergistes there, meaning that means that they're just getting translocated. I told you that we're going to talk about the mouth microbiome. So the mouth microbiome and the gut microbiome, they have a certain degree of overlap, actually 45% in composition. It's overlapping between both ecosystems, but there's certain differences in terms of abundance. When you start seeing very high amounts of bacteria that are more dominant in the mouth than the gut from these overlapping groups, we start seeing a pattern there that most of the times can be related to a translocation problem, meaning that we are swallowing bacteria, but those bacteria, instead of getting killed in the stomach acid or through the bile acids, instead they're getting in large amounts into the GI tract and maybe even colonizing and staying there for good. That also implies that we're probably mimicking the environmental conditions between the mouth and the gut more closely, which is something that always happens when we start producing less bile and we start increasing the oxygen levels in the gut, which is not good because we want to be anaerobic to a certain extent, and actually we want to be very anaerobic in the colon, and that's needed to be healthy. So we start matching the oxygen and the pH levels in both ecosystems, and now these bacteria are actually surviving and even maybe thriving in the gut where they're supposed to get killed and just die, not really living there. Synergistis is one of those groups. It's a large group, gram-negative. Actually, it's pretty pathological in the mouth as well, if it's in large amounts. So we probably wouldn't even want to see this type of groups too large in the mouth as well. So now let's go back to Archaeota, this person with low efficiency, and that one of the main things that we have low efficiency typically is stomach acid production. And now let's say this same person now has this synergistis found in the sample. Well, we have now two findings that are telling us that the digestive efficiency is not optimal, and that might be something going on there. Now, I always look at this with a little bit of toxicological analysis in my view. The reason is because some of the most important disruptive agents for digestive efficiency are coming from the toxicological world, including organophosphates, mycotoxins, and heavy metals. So I always get suspicious when I start seeing these things that we might be dealing with some degree of hypertoxicity that is driving lack of efficiency and altering the patterns in the composition of our bacteria. Keep that in mind. It's not rare, by the way. It's very common. So yeah, I always like to have a toxicological analysis on the side. If this is also something that can happen with a typical SAP diet, that also can happen with high levels of stress. But to be fair, all those things are also driving toxicity. So it might be more than just one thing. It might be a combination of factors driving these imbalances. The other group I like to see always is Ascomycota. Ascomycota relates to mold and comprises like 33,000 types of species of mold in that group. Now, we don't have the specific information here, but we can see if the person has some positive findings for mold. Now, one thing that you always have to be aware when you're looking at this type of reports and you see Ascomycota elevated, before screaming and saying, oh, do you have a mold colonization in your gut? Ask if this person was taking Saccharomyces boulardii that is typically found in multiple probiotics. If this person was taking Saccharomyces boulardii, that S. boulardii is part of the Ascomycota phylum, and it will be detected there, and it will be, of course, elevating the findings of Ascomycota, but it's not really a bad thing, just a transient mold that we're using for trying to improve the gut in a certain way. So that's something we need to ask all the time if we have Ascomycota. If it's not, that if that person was not taking anything, well, yes, we probably need to worry a little bit. And maybe I will do some mold testing on the side to try to figure out what's specifically going on there. Now, the other one that I want to mention from this list is Fusobacteria. And Fusobacteria is critically important. Fusobacteria, it is a mouth group. It's not a gut group first. But it does something when it's present in the gut that is very concerning. So there's a lot of studies right now about Fusobacteria connected to IBS, but it gets worse because the Fusobacteria presence can actually drive more emphatically the overproduction of hydrogen sulfide. Hydrogen sulfide, another gas we measure for C. Hydrogen sulfide has a good side and a bad side. The good side of hydrogen sulfide is that it's actually pretty healthy if it's produced endogenously, meaning that our colonocytes are producing normal amounts of hydrogen sulfide. Sometimes our colonocytes are not able to produce enough. And because of that, we might need to use a little bit of the exogenous production of hydrogen sulfide that comes from different types of bacteria, which are sulfur-reducing bacteria. In good combination, we have a healthy metabolic turnover, good metabolic activity of your mitochondria. So we have really a lot of benefits from having good amounts of hydrogen sulfide. The problem comes with elevated numbers of hydrogen sulfide being produced. Now, if that happens, we actually do the opposite in the colonocyte. We reverse the metabolic activity of the colonocytes. We start halting all the replication of the colonocytes, and that ultimately leads to IBS or inflammatory chronic illnesses in the gut. Now, when we have that situation and Fuchsiobacteria shows up, especially one species called Fuchsiobacterium nucleatum, which is pretty nasty in the mouth as well because in large amounts can drive more complex conditions of periodontal disease. If it's now showing up in the gut, it will turn inflammation into neoplasia. And that is one of the most important risk factors for getting colorectal cancer. So we don't want this guy to be in the mouth, in the gut. We don't want this guy to be in the mouth in large amounts, but we definitely wouldn't want this guy to be in the gut, especially if you already have some other markers related to hydrogen sulfide. So long story short here, if you see this, that means that you're translocating this microbe from the mouth, most probably. And if that's the case, you need to cut down from the root, improving your digestive efficiency in all the ways possible, improving the stomach acid barriers, and of course, using certain strategies for counteracting the overgrowth of Fuchsiobacteria. My preference usually are immunoglobulins, usually bovine-derived immunoglobulins, and spores. Those are quite great for balancing the overgrowth area. There's other things, but this is not a treatment plan class, so I will stop there for now, but just keep an eye on this. So when we analyze the composition, and we already saw the phylum level analysis, we know that we can also compare groups to another groups, and we have something called dysbiosis ratios. These are not accurate, and they might also sometimes will give a misleading idea of certain things I will explain right away. But in many cases, they can give us an understanding of the person's diet, the person's diversity, and the person's risk factors for gaining certain metabolic conditions. Now, for the main one here is Firmicutes-Bacteroides ratio. And Firmicutes-Bacteroides ratio, because we're comparing the two largest group in the gut, is critical to understand. They tend to have more Bacteroides than Firmicutes, and therefore low FB ratio. If we have high Firmicutes and low Bacteroides, that typically relates to people that are unable to lose weight more easily, or that they're on SAP diets, or they're just not getting a healthy type of diet, or that they were using something that was affecting their diversity. But typically it's more dietary. The Firmicute elevation also has been found to be correlated with the presence of certain toxins. So also that can be a marker of toxicity. And that actually explains why a lot of people that are toxic, they can't lose weight, because they have affected populations of microbes due to that toxicity. We don't want to be in any of these extreme situations, either low or high. We just want to be between 1 and 1.5 in the ratio between Firmicutes and Bacteroides. That's your ideal place to be. Anything above that or anything lower than that might be a little bit of a risk in terms of the assessment. There's other ratios, but I'm not going to mention them right now. They're not so relevant. I think this is one of the most important. By the way, before I forget, because we're dividing one number to another, of course, if we amplify one too much and we lower the other one too much, that's going to be reflected in the final result. What happens if we amplify a lot, both sides, or we diminish the amount on both sides of the equation? We might get a healthy ratio regardless. Because of course, you can divide 100 to 100 or 1,000 to 1,000 or million to million, you're still going to get the same result. So careful with that. In some cases, we see totally abnormal populations of microbes, but because they were both amplified in the same way or diminished in the same way, we get a healthy ratio, but the composition is completely affected. Check that before making conclusions if you're looking at the ratio, because that might lead you to a misleading diagnosis or misleading interpretations. Now, the other thing that we see a lot in the analysis of microbiome is pathogens. Now, pathogens, I think, is a very unfair term. A pathogen is something that is more from the germ theory, and we know that no bacteria can actually kill us or make us sick unless there's a terrain that is allowing that microbe to thrive. So it's never the microbe, it's always the terrain. I like to emphasize that every single time because we disrupt terrain and then opportunistic microbes show up and we start blaming the microbes. And if we start killing those microbes over and over, we're just going to get things worse because we're not really fixing the root cause. We're just affecting more and more the terrain, and these potentially pathogenic species are going to come back worse and worse over time. So keep that in mind, please. This is, I think, is a very important thing to. But that's something that we like to see. And there's some things that are commensal, and some commensal bacteria are expected to be in the gut, but in certain amounts. If we see too much of them, that leads to the understanding of we have a certain alteration in the terrain. Some other guys are just not supposed to be. Some pathogenic species are very hard to be detected because of the methodology on the way we are doing the metagenomic analysis. Because remember that for doing metagenomic analysis, we need to expose the genes. That means breaking the shells and exposing those genes, but not all the microbes, they have the same thickness in the shell to expose those genes. So sometimes we need different types of processing, and because of time and cost and a lot of reasons, we can be doing a different processing for one single sample to open up all these different microbes in the proper way. So we might miss a few things, and that is actually typical and it's fine as long as we can open the most amount of microbes for their detection. Now, I will say that everything can be a pathogen or everything can be a healthy commensal depending on the abundance and the location. And therefore, we need to keep that in mind. There are certain bacteria, for example, that I will mention now, for example, Saccharolytic westwardensis or Bacteroides fragilis, or which the other one that I'm missing. There's a few others, but they're actually thriving on saturated fats, and they can protect themselves from bile acid activity, and they will tell you that you have some issues in terms of emulsifying the fats. That's why you're overfeeding them and they become larger than they're supposed to be. That's one way you can grow a commensal bacteria into a more pathogenic type of bacteria. E. coli will fit in the same category if you are unable, for example, to activate the iron supply from foods, and that's going to become more a food for E. coli than you, and E. coli is going to compete for that iron supply, and it will become overgrown. Or you might be even getting a supplement with iron that is not really bioavailable. So we have to be careful. Those bacteria are supposed to be in the gut, but they're not supposed to be that much. There's some other bacteria that are not even supposed to be there, like salmonella, for example, and that means that we have something going on, or we're getting exposed to something that is not supposed to be present in the gut. So make that difference, of course, when you understand the analysis in terms of the pathogen. Now, the group of bacteria we see for potential pathogenic species is quite vast. I like to just know which ones are supposed to be there in certain amounts and which ones are not supposed to be there in certain amounts. If we look at, again, Bilophila westworthia, or Saccharolytic westwardensis, or Bacteroides fragilis, those things are mostly commensal. E. coli is commensal bacteria. Those things are supposed to be there. But other things, like, for example, Vibrio cholerae, or Salmonella enterica, or Campylobacter, they're not really belonging to the gut microbiome. And they're telling you that we're getting some contamination, mostly from other sources. We have most also protists and fungi as well that can we detect, and viruses. And again, remember that microbiome is a very complex ecosystem, and everything can be in the mix. It's just all about location and abundance. That's the most important. And that all these microbes at the end of the day can promote virulence factors and try to activate the host immune system in one way or the other. But the microbes itself, they're just going to interact with the rest of the microbiome, but is the toxins, the bacterial toxins, that they will drive a more acute condition. Some people, they live with these microbes for their entire life and they don't even know. And so we might have a very high amount of pathogens or a certain pathogenic species in your gut. And as long as your immune system is not detecting that, or this bacteria is cloaking from the detection of the immune system, whatever is the case, is using biofilm measures or anything else, you might be living there and you're not feeling sick because of that, at least not dramatically sick. As long as the moment we start poking that bacteria with antimicrobials, or the moment we're trying to rebalance the microbiome, or just because we got directly these bacterial byproducts, which are called toxins from a contaminated food, then we can get more acute reactions. And those are the ones we see with acute diarrhea or vomiting or very acute stomach pain. So I will say that for now, it's most important to understand that not the sole presence of a potential pathogenic species drives illness. It needs to be correlated to an immune reaction. Another thing you're going to see typically on the analysis in the microbiome is functional keystone species. And functional keystone species are species that they promote functions in a very specific and very efficient way. So we kind of rely on the presence of these microbes to improve our efficiency. And some microbes, denominated keystones, are overlapping in functions with other microbes. Some others are quite unique, like Akkermansia muciniphila. We just can't replace them. We need to have them. Akkermansia muciniphila, I will stop there for a minute. So the Akkermansia muciniphila, it's a microbe. This is a bacteria that is strict anaerobic and that is typically living at expenses of the mucosal layer. So what it does is that mucosal layer is divided in two. We have a mucin 2 layer, which is pretty thick, pretty like solid, more solid. And then we have mucin 1, which is more fluid and it's allowing the intestinal transit and gives us a lot of other benefits. Mucin 2 layer is promoted and regulated by many species, including Akkermansia muciniphila. Akkermansia muciniphila is going to send signals to the colonocytes, to the goblet cells for producing more mucin. At the same time, it's going to use the mucin 2 layer as a substrate, as a food substrate for survival. So degrading mucin and at the same time is promoting the production of mucin. And that leads to a constant thickness of the mucin 2 layer, which is amazing for protective reasons, for the gut lining, and immunological reasons for the immune system, and digestive reasons for allowing the normal passage of foods from one side to another. That's great. But as I said before, it's a strict anaerobic, meaning that needs low oxygen. How we get low oxygen level in the gut? Well, the best way is fermentation. Fermentation, as a biochemical process, uses the oxygen in the environment as a catalyst. And at the end of the reaction, it won't give you back that oxygen. So the more you ferment, more oxygen you're scavenging from the environment and therefore lowering the oxygen in the gut. So especially in the colon is where we ferment the most. And therefore we should be reducing the oxygen level there the most, which is great because that's where the mucin 2 layer is always the thicker, and that's where Akkermansia muciniphila should be. Let's say you want to try to put, for example, a probiotic containing Akkermansia muciniphila. And let's say for a minute you're successful in bringing all through the old barriers and other type challenges in the intestinal tract, you're able to put that microbe alive in the colon. If it's not low oxygen there, if there's no low oxygen in the first place, it's not going to survive. That's it. It's going to die anyway. So Akkermansia needs very specific conditions. So for improving Akkermansia muciniphila, what is the best way? Well, lowering the oxygen in the colon. How you do that? Increasing fermentation. How you improve fermentation? Well, improving the functionality of your digestive organs, meaning that you're going to produce more enzymes and more, and you're going to also eat more fermentable foods, which are typically fibers. And so if you improve the amount of intake of these non-digestible fibers oligosaccharides, etc., that can be fermented in the gut. And also you improve the capabilities of your body for breaking them down and actually utilizing them and making them fermentable. Well, then you have the perfect combo. Now, also you need to increase the diversity of your microbiome there, and that's where we can use certain strategies for that. But just at the end of the day, you want to improve fermentation because that's the only way you can lower the oxygen, and that's the only way you can make your Akkermansia cinephila thrive. Nothing else will do. So that's a takeaway of now that you can try to utilize for improving Akkermansia cinephila levels, and not really relying on just a straightforward inoculation of Akkermansia cinephila in the form of probiotic. Because again, it's very unlikely you're going to get long-lasting benefits. You might get some transient benefits, but not the long-lasting you're looking. You don't want to be in a supplement for all your life. You want to be in a supplement, hopefully, for just enough to make things better and then stop it. That's at least my philosophy in terms of supplementation. Now, going back to the process that happens in the gut, we have a saccharolytic fermentation pathway and a proteolytic fermentation pathway. We need both, but protein fermentation becomes a little bit more complicated when it's elevated, because the byproducts that can be created through the protein fermentation can become very inflammatory for the gut if it's too much of them. Carbohydrate fermentation is a little bit more, we'll say, gentle. It doesn't really create too much issues, but that also depends on where you're doing these processes. Keep in mind the small bowel is mainly made for proteins and fat absorption. It's not really related to carbohydrate fermentation. So carbohydrate fermentation should occur in the colon. And again, remember about location and amounts. If you have low efficiency in your digestive pathways, you might start fermenting carbohydrates in the small bowel, and that's not right. That's not what you want. Or you don't want to start fermenting too much proteins in the colon. That's also not a good scenario. Anything like that will create disruption in your health, in your GI health, and ultimately symptoms that you're not going to be enjoying. Keep in mind, things they should happen in the place they're supposed to be happening. So that's something that only can happen if you have good efficiency in your digestive pathways. Now, we need both pathways. 70% of the microbiome of the gut is a carbohydrate fermentative group of microbes. You won't get that type of fermentation on an exclusive carnivore or ketogenic diet. We thrive in proteins, and don't get me wrong, and fat, but we were thriving through those nutrients in an on and off way, not permanent, because we were adapted to seasons, and seasons, when they became cold, we needed to hunt. There were no plants or anything else we could eat. But in summertime, we were thriving on plants and fruits and vegetables and spring. Well, but again, we can go on and off, and that's amazing for our metabolic needs. Too much of a good thing becomes a bad thing. And that is in any of these extreme type of diets. Your microbiome needs carbs, period. There's absolutely no question of it. There's no way you will ferment proteins in a way that they're not going to compromise your gut to create the ecosystem and the nutrients needed for the rest of your microbes and for your own cells. Now, again, careful with the proteolytic fermentation, because that can become tricky if it's too much. There's some byproducts that we can't handle in large amounts. Now, there's a couple that I want to highlight right now. Ammonia, for example. Ammonia, it's also highly alkaline. Now, what is the main buffer of the gut? Bile. What if we're deficient in bile production for many reasons, including hypertoxicity, stress, and all things that can drive endotoxemia, anything that can drive cholestasis? Well, our microbes are trying to survive, and therefore, if they're not getting the buffering from bile, they're going to produce something else. So we can highlight ammonia for that purpose. Ammonia, of course, is toxic for the kidneys especially, but it's a compensated measure if we're not producing enough bile. Hydrogen sulfide, I forgot to mention, and it's also toxic scavenger molecule. So certain toxins can be scavenged out of the body with the presence of hydrogen sulfide. Again, that could be a very useful tool for detoxification, but also has some downside. Nothing is a perfect thing. It's always about balance. So again, if we're putting too much toxins in our body, then we will create a challenge. The challenge can be compensated, but it's going to be a collateral damage as well. So look at that angle when you're looking at these markers, because we might see more than just what meets the eye initially in terms of these findings. Now, the short-chain fatty acids are critical, and those can be produced through mainly carbohydrate fermentation. We can produce butyrate through the conversion of acetate. An acetate can be made out of protein and fats. So we can use fats and proteins to produce acetate, and acetate then, through the function of a keystone species that's called Faecalibacterium promnitzi, can be converted into butyrate. So we have an alternative pathway for producing butyrate, but we don't have to stay in that pathway all the time, because we know Faecalibacterium promnitzi, if we're overfeeding that through the pathway of acetate, because there's a necessity to produce butyrate when there's a lack of carbohydrate intake, that can also drive a lot of immunological reactions. So we don't really want that. So a little bit is fine, compensating in the compensation mechanism. Too much is going to overwhelm the immune system, and it's going to get nasty. There's a lot of autoimmune skin reactions and other things that are driven by an overgrowth of Faecalibacterium promnitzi. Now, I will not go into the specifics of each short-chain fatty acids. That's, I think, is a very long topic that I don't think is necessary for now, but they're very relevant for health. They're very relevant for immune health, for functionality of our gut, for the functionality of our brain, for mitochondrial functioning, for the normal replication of our colonocytes, so therefore the integrity of our anatomical structures. There's a lot of things that we rely on from the short-chain fatty acid production. Now, there's another thing I've been talking about, which is the Estrobolome. Estrobolome became very trending. The reason why, because there's a lot of hormonal imbalances. And trying to find the root causes of the hormonal imbalances, well, we'll look at the microbes now, and we know that there's a group of microbes that we denominated Estrobolome, and the Estrobolome will be related to the deconjugation of estrogen that then will be recycled and will be brought back to circulation, and therefore increasing the estrogen levels and, of course, potentially driving estrogen dominant. So it looks like a really bad thing for us, especially for hormonal health in both men and women. And it seems like we should not go through this process, and we should be eliminating our estrogen properly. Like I said before, there's always a certain degree of balance in these equations. Beta-glucuronidase is true. It's made by this group of microbes, and it's a deconjugating enzyme. But we're not deconjugating something that was already conjugate just for fun. There's a reason why. So I want to explain this in detail, because this might give you so many tools for understanding what's going on with your patients. Deconjugation comes as a scream for help. It's the body that can't handle this already conjugated molecule to be excreted out of the body. The simple way that I can put this: you have something that went through the conjugation pathway, was binded to an amino acid, and it was ready to leave the body, and then something said, please don't, stop, I can't handle this. Bring something in, cut this bond, release this molecule, and send it back to circulation. The reason why is because detoxification is not happening in the proper way. It's not working in the right way. And that could be because the directionality of the whole detoxification system is upside down. Maybe phase 3 is not working properly, and therefore the body's sending a negative feedback, telling the conjugated molecules and the enzymes managing them, cut this, bring it back. And remember that beta-glucuronidase will deconjugate any conjugated molecule of estrogen but also can deconjugate many other molecules that go through the same pathway. And that means mainly toxins. So we know that beta-glucuronidase activity, it is related to the estrogen molecules, but also to many other things, which we're not really talking about, that actually we call Estrobolome because we are so connected to the estrogen part, but there's so many other things that are related to the same activity of these bacteria for other molecules. And again, this is, for me, a sign when it's elevated of hypertoxicity, and therefore a stagnant detoxification system that needs to be improved. And that is probably one of the critical root causes for estrogen dominance, along with many other hormonal imbalances. Remember also that all the hormones are made by an initial molecule called cholesterol. So, and that is also made in the liver. So it's all related. So I think this is something we need to look with a different angle, just not saying, oh, these bacteria are creating the estrogen dominance, which is true, but not entirely true. We need to look at why these bacteria are producing more beta-glucuronidase, why they're deconjugating these molecules, and why they're sending them back to circulation. And it's not just because there's a reason why. So I want to finish this right now. I think I cover a lot of things that are related to the biggest questions I get from the microbiome analysis. These are probably one of the most important aspects where you can make a difference. I don't want to cover the whole microbiome analysis as in full. It will take me 3 hours or more probably to cover that, I think more. But these little pearls that I just gave you, they can give you a different angle and a different direction, not only in the assessment, but the treatment plan. These might pose some questions in terms of, does this person has hypertoxicity? Does this person is in risk for colorectal cancer? Is this person is affected in any of the digestive support organs, or is producing enough stomach acid? Or maybe there's some dysbiosis in the mouth that needs to be assessed. So there's so many things that I think we can get from these pieces of information that are so valuable to be more accurate in the way we see our patients and we help them. So I'm hoping that this is going to be helpful for you as well as it is for me any day of the week, and that it will give you these insights that are so needed, because this type of analysis is complex. I know that, but it's only by repetition and getting more and more information from people that are doing many of them on a daily basis that we can really expand our knowledge about these type of tools and make them more useful for understanding our patients' needs. And I do think that this is a tremendous tool if it's done and utilized in the right way. Thank you so much for listening to me again, and it was a pleasure. And I'm hoping that I will be talking to all of you again soon. Thank you.
Welcome to Rupa Health, the best place to order, manage, and track results from over 30 different lab companies in one single place for free. It's going to take you under 2 minutes to sign up, and you can order any functional medicine lab for your client in under 30 seconds. Let me show you how it's done. So here's our beautiful interface. I'm typing in the name of my client, selecting the lab that I want to order for them, and hitting send. From there, Rupa and their amazing team handle the rest. They email the client, collect payment, and even offer an interest-free 3-month payment plan. We've also built the world's largest library of information about chronic health conditions, the lab tests that can help you find the root cause, and the evidence-based interventions that you can use to help people heal from them. It's called the Rupa Health Magazine. There, we have in-depth articles about almost any health condition you can imagine. And we give you step-by-step protocols that other clinicians have used to help their clients heal and that are verified by evidence-based sources. You should totally check it out, and it'll transform your practice. And we can't wait to see you. So make sure you sign up today at rupahealth.com.